Thumbs up.
All right. So welcome to another life science stream today. We're going to be talking about infrageometry, some of the ideas that we wanted to implement, and might be a quicker one since I've been very busy with other things, and I think I mostly wanted to run some thoughts and some ideas. And yeah, we can look into maybe live coding a little bit the homotopy of a torus. I think that could be our sort of stream activity. And yeah, just keep moving along. So let me bring that up. All right. So I'll do a very brief recap of how we are approaching homotopy, because it's going to be sort of a living example of the constructions that we want to do in Infrageometry. So if Mathematica works, right. Okay, so sharing the screen. Okay, so you can all see this, right? So this is the points from last time. Remember that we are going to self-impose a few constraints so that our investigation is a little bit more complete. So we are only going to use graphs as our spatial information. We are going to try and exploit as much as possible the metric distance on graphs, meaning just counting the number of edges that you can find in a path, and then the fact that for any finite graph you can always find a minimum of such distance. We want to think of functions as numerical value assignments to nodes and edges, with the flexibility and kind of prototype sense of anything goes at first, just to get some notions rolling. Of course, noting that there's no pre-existing embedding space, so we are not really implying that any of this information is intrinsically spatial. So everything that is spatial must be emerging from this. And the idea is that eventually we'd like to take large cardinality limits. And I say large cardinality, meaning broadly, we might want to make things big and run for long and things like that, and they need to make sense. So the main goals of the project right now are to get Riemannian geometry constructions, to get homology generally, to get fiber bundles, and to get something like symmetry transformations. So we're going to look at homotopy today just to have something concrete to think about, but it would basically show the essential approach that we're taking with this. So, okay, so how do we look at homotopy? So if we have the notion of a graph that represents our space, and we want to consider, oops, I need this code. Maybe that's all. Yeah, so if we want to represent two ways of navigating this graph from a 1 to 7, you can see that there's many different ways. If we restrict something that has length 3, then there's these two paths, for example. And then we want to think about the possible the possible ways to form a path, thinking in terms of homotopy. Remember this idea that you can continuously deform the path and not change the fundamental topology. We want to think of it in terms of 3 rules. So first is what we call a shrink, which essentially we are doing the transitive completion of a path. Then we have the bulge, which is the opposite of that. So in some technical sense, the inverse operation, where if you have a path that can be longer between in a minimal sense, then you take the longer route. And then so this is obviously a reductive rule for paths. This is a additive or generative rule for paths. And this path form, which is the one that more sort of squarely represents the homotopy transformation, is just conservative. It doesn't change the amount of edges in paths. So to illustrate this, we take our path here, and where they have, yeah. So I take this thing, and I'm not going to run it again because, yeah, it's big. We don't have to wait. So I apply these 3 rewrite rules, as you can see here, the bulge, the shrink, and the deform, to the homotopy graph 1, which in this case had the path going 1, 2, 6, 7. And so as you can imagine, the rules are going to apply, and it's going to push this yellow path to maybe go from 1, 3, 6, 7, or it's going to make it shorter and just go directly from 1 to 6 and things like that. So those, so we do it for 3 generations, just to apply at most 3 possible steps, which this means is that you apply these 3 rules in all possible ways 3 times. So it could be 3 times the bulge, it could be 3 times the deform, it could be bulge, deform, bulge, it could be, all possible combinations of 3 rule applications. And of course, we get, expected. The style of the curve is lost here under the rewrites, but you can see that, for example, here we obtain, this is just the initial state. There's nothing done, but here, for example, we can see that there's been a bulge applied to the path between 1 and 2 here. Now it becomes a path between 1, 3, and 2, right? And the rest is unchanged. So eventually, so here, for example, we have a homotopy deform that is pushed the path to go through 2 to go through 3. And then, of course, we're going to find some instances like this one, for example, that is actually the same path, right? Which is to be expected, since path deform applied twice does nothing, and bulge and then shrink, or shrink and then bulge does nothing when applied on the same site, on the same matching sub graph. So eventually, the whole point of this is that after all these are all the possible ways in which you can apply these three rules up to three times. Eventually, I think it's the last one. Scroll all the way down, you do find this state, right? You do find a path that goes from 1 to 5 to 6. And so, in fact, you can think that this is precisely the case where the homotopy, the form operation, has been applied 3 times in a row. That's why it actually appears at the very end of the list, because it corresponds to that. And so this particular state, we can just extract and then realize that, this is this state copied over here. I can just delete these 2. I don't need this right now. And I can simply ask, all right, my other path, right, that I had, which was from 1 to 1, 5, 6, 7, is it isomorphic to one of the states in this big list? And of course, we can just parse the whole list, but just to show it more explicitly, we take this one here, copy and paste, do it here if you want, and this leads to true. It's the way we see the. In fact, I have the old embedding here. I'll just collapse over here. I'll take the path that we're looking at, which is this one, and I'll put it in the right place. And here we go. But yeah, it's very clear that these are isomorphic, so good that we have a function that tells us that that's the case. All right, so with this, this is where we left last time, and we would like to extend this to more of a realistic mathematical setting. So in particular, we want to look at the quintessential non-trivial homotopy object, which is a torus. And so we would like to have a way to express the fact that a torus has sort of a handle, and there are some curves that you can collapse into a point, but others that you can't, and so on. So I was one of the things that I tried to do is I was trying to represent a torus with a graph. Now, remember that these two rules, and this is where I'm going to collapse all these things, because obviously I don't want to be scrolling all the time. So in a moment, I'll just collapse this. Maybe smaller. In fact, I don't know what's here. So these two rules, sorry, these three rules, as you can see, they apply to fairly specific subgraphs, right? So if you notice, these three rules that don't say anything about what happens when you have a square or in a graph, right? So when you have something like this, I think I can. So if you have a graph that looks like this, 1 to 2, oops, then 2 to 3, then 3 to 4, then 1, right? If I have this kind of graph, I can move it. Yeah, it's nothing really can happen if you have a path between these 2 points, because these rules are never going to apply. Why is that? Well, notice that in all these, in all the inputs of these rules, you see that there is a triangle of undirected edges, right? There is a undirected edge triangle that, and here is in fact 2 of them. So at least there is one undirected edge triangle. And so, of course, this graph has no undirected edge triangles. So no rules are going to apply to this. So it doesn't matter how you draw your paths on top of this graph, you're never going to have something like a homotopy deform. So this is the case, for example, when you do just the torus graph that is currently in the language, you get a graph that is basically all it's a torus that is discretized with squares, which makes sense, or little rectangles, which makes sense because that's kind of the coordinatization of a torus. So this is a discretized coordinated torus, right? Or coordinatized torus. So one could get a simplicial version of this. So simplicial means that your element of surface is always going to be a triangle. So you can get your edges to be triangles, and you can get it with the right function here. So in this one, as you can see, there's edges that connect basically the squares in here. They are connected also through the diagonal, at least one diagonal. So now the topology of the torus is captured with triangles. So this is really the graph part of a triangulation of a torus. This is not a triangulation of a torus if you take it as a simplicial set. This is a triangulation of a torus, and it's just the graph component of the triangulation of a torus. So an actual triangulation of a torus is a hypergraph. It's a simplicial complex, so it's a very special kind of hypergraph. But because we are under these constraints of just graphs, so we look at simply the graph.
Just to be clear, the two-dimensional printout, the previous figure of the torus, that has quads, right?
This exactly. So the discretization here is made by essentially taking the coordinate curves of a torus, right? By that I mean if you parameterize your torus with two angles, right? A torus, as you all know, is just S1 times S1, circle times a circle, Cartesian product, right? So if you times the two circles, if you discretize your circles, so you have two cyclic graphs, and you just take the direct product of these graphs, this is the graph that you obtain, right? Because you can see that each, for each quote unquote coordinate value, meaning at its angle value, discrete angle value, you have a cycle graph, right? You have circles that go around, and you have circles that go in the
right. It's a rectangular mesh wrapped up.
Yeah, and it is a rectangular mesh. So I mean, it's visually obvious. It's just clear that it's a rectangular mesh. I'm just saying that the reason behind this is that the reason why I imagine the language just outputs this, it says, you know, a torus graph and it gives you a rectangular mesh, is that it is very easy to discretize a coordinatization of a torus, because a torus is technically a circle times a circle, and the circle is just a cyclic graph in a discrete sense, right? So, but that's not good for us, because if we want to,
it's also just a quick comment. It is also generalizes the torus into high dimensions. So it's basically just circle times circle times circle.
Correct.
Right.
Absolutely, exactly. Yeah, that's exactly right. So a torus generally, when mathematicians speak of a torus, they normally don't mean a two torus. They mean a n torus for n, the number of circles that you're multiplying together, right? So anyway, so this was something that I had to deal with, because this implementation of homotopy only really works. So this is, you could think of this as the simplicial implementation of homotopy, where you're assuming that your spatial graph is at least will have some regions that have a simplicial-like behavior, and that's why we're using triangles as sort of the atomic notion of this. Because otherwise, you would have to write very many rewrite rules for each of the situations, right? You would want to say, actually, a sort of square of edges is also good enough for my homotopy. So you would write just this rule, or sorry, just this rule, but maybe leaving out the diagonal in the middle. Or maybe you want to say something much stronger. You say, no, you want the two diagonals, and then only you can make this change. You know, there is choice here, right? Like, it's important to note that when we go into this sort of infra world, there is things become more choiceful, right? They become freer and with less constraints. But anyway,
yeah.
So
yeah. Like, you know, one thing to try next, I guess, would be to say, what if you're looking for an arity 3 hyperedge on that triangle before you were allowed to pull a chord over it?
Right. So and this is the natural thing to do, but we are working under the constraints given by Stephen. I think that's the kind of the exercise. I'm not saying this is the ultimate story, but the working under the constraints that we only do graphs for at first, right? We have to somehow emulate surfaces, because obviously the natural thing to say here is that you can only homotopy the form when you have in fact a triangle within this, right? Like, basically by saying, I can do this very quickly visually. So by adding here a 1, 2, 3, and I guess in the output as well. Right? So this is a natural thing to do, but we are essentially going to stay away from bringing in higher arity edges for now, because given the constraints, then we need to exploit as much as possible the other two. So for now, I'll just use the graphs and see how far we can get. And I think actually for homotopy, you get the full story, because there's no sense in which this sees surfaces in any way, because it's just paths. I mean, if we were to do homology, higher homologies, then probably we will have trouble, because I mean, honestly, I don't know how we're going to see. I mean, Stephen has this idea to do surfaces with spanning sets of paths, which honestly, I don't think it's the best idea, but it's something that might work. And it's statistical from the ground up. So you won't be able to just see atomic examples like the torus, which I think is a disadvantage. But anyway, so we have to find to do the quintessential homotopy example. We have to find a torus that somehow has a graph form that is workable. So this is a torus with a graph form that is workable, but it's quite big. So doing operations in this will be a bit heavy. So instead, what I thought is like, I'm gonna try and represent a torus in the smallest possible triangulation. So there's always such a thing, right? If you have a manifold oriented surface, to be much more specific, there is always a smallest triangulation, right? So if you think, for example, of our favorite oriented surfaces in the known to us, right? So which are these? These are a disk or just finite plane surface, a sphere, torus, things with larger genus and so on, Klein bottle and things like that. Klein is not orientable, but whatever. So if you think of these, for each of these, there is a minimum triangulation. So let's go for a few examples. So what is the minimum triangulation of a finite plane or disk? That's just a single two simplex, right? It's just a triangle. So you have a minimal surface. That's it. That's a triangle. Now, what is the minimum triangulation of a sphere? Well, that's a tetrahedron. So you need 4 triangles in this case to represent a sphere. Now, what is the minimum triangulation of a torus? It's basically this, right? And as far as I know, I think this is the right thing. This is the minimum triangulation. So it looks very weird here. I mean, it's hard to see a torus here, but actually, if you know the topological definition of a torus, a typical sort of textbook definition of a torus, you can actually kind of already see that this is going to be a torus. But I'll get back to that in a second. So before we see that, we can actually embed. So what I did was a bit of good old Euclidean geometry. Going back to high school, I had a lot of fun just computing, applying Pythagoras theorem by hand and things like that, and then actually being able to render it here. So the way that we're going to do this is we're going to I want to build 3 triangles like that. These are going to be kind of the base, the lid, and the middle, the hole for the donut, right? So think that I'm trying to build the smallest donut with triangles, right? That's the game here. And I define all these things, which they come from just drawing that I want an equilateral triangle, and I want this to be 1/3 of a unit, and when the length of the thing is the unit, I mean the side of the thing is the unit. And so with this, I just draw. You go on your either in your mind's eye or you draw, and you think, okay, so these are going to be, by the way, the vertices of these triangles are the vertices of the graph, right? But forget about it. The triangles themselves have no meaning. They're just for visual aid. And so what you do is you fit a triangular torus between this. So you go from this one, you're going to trace a line to there, and then to there, and then to there. So the way this looks is you just create, you define this as a graph, and then you make it graph 3D, and this is what you get, right? So you can note that there's a hole, right? That's the hole of the torus, and then there's basically 3 faces that's in the outside. So if you think about it, it's kind of like smallest circle. What is the smallest circle? Well, that's a triangle, right? That's the smallest discrete circle. That's a triangle. And so the way the connections work out is that each face that would be, note that the section of these, so what is a torus, right? A torus has a circular section on the sort of ventral direction and a circular section on the zenithal direction. So each of these are going to look like cycles. So each cycle will be discrete, and I want them to be the smallest possible cycles. So they are all 3 cycles or triangles, right? So note that I have a section on this side. This is the sort of zenithal section. That's a triangle. And then I have a section on the horizontal plane that is by projecting like that. And so that's a triangle. So that's why you get 3 triangles in the horizontal planes, and then 3 triangles in each of the corners of those 3 triangles, right? And then all you do is, oops, sorry, just did a cool flip there. You basically join the faces that would be rectangles, and you turn them into triangles. But you do so minimally, and it's quite easy to follow that all you do is basically you start to trace larger triangles that fit into the torus. So, for example, you go from this along this edge here, and then you continue along this edge over here, and then along this edge over here. So that's another triangle that you have. So basically, long story short, this graph over here, which is not super small, but it's much smaller than this, obviously, it contains the same topological information as a torus, right? So good stuff, right? Like that's the point. So why? But I mean, this kind of looks messy, right? If I were to show this, can I just small? Yeah. So if I just show this as a 2D graph, no chance of seeing that this is a torus, right? Like it's really difficult to see from this embedding. However, with this other embedding, if I do the grid embedding, actually this looks like a torus. And why? Well, remember that you can think of a torus. There's several ways to think of a torus. We said it's S1 times S1, but if you think about what S1 is in turn, you realize that S1 can be understood as an interval that has the endpoints identified, right? So it's basically this idea that you can move along the interval as long as you're in the middle points. That's okay. But the moment you get to one of the endpoints, you actually have a quotient rule that tells you that you should go to the other end, right? So if you take a Cartesian product of those two, that basically looks like a square where the sides of the squares are identified, one to one in the opposite sides and preserving the orientation. So in this sense, forget that this is a graph for a second, just think that this is a square on the plane, right? The idea is that you have the sort of bulk interior of this square, the region of the plane, to be just proper points of your torus or your surface, and then the points along the sides, so the boundaries, are identified one-on-one with the opposite sides. So all these points over here are identified with this, and all these points over here are identified with this. So this is kind of a familiar picture that you can, if you had a rubbery material, not paper because it's not really elastic, but if you had some kind of rubbery material, you could deform it in one direction, a rubbery square. You could deform it in one direction to make a cylinder, and then you could deform it again to join the two ends and make a torus, right? So that's kind of the idea behind this. And so when you represent the graph like this, you realize that what the edges represent, the pairwise edges of a graph represent on a surface are minimal paths, right? These are sort of the atomic paths that you can build. So if you actually follow the paths implied by these edges, they exactly correspond to the paths that you would have in a torus. So for example, if you follow, I mean, obviously the sides, that's clear, right? Like you have the 4 sides, you have the 2 middle sides, that's fine. But if you, for example, follow this path, you go this edge, let's go along this line, you come here. If you're going in that direction, then you should jump to the opposite side of the torus. So you jump over here, and then you continue your path, you're over here, and then here you should jump to the opposite side of both. So you have to go to the opposite side of your square. So now you go to this side, right? So you realize that actually these 2 edges in this diagonal with the same incline actually represent the same circle curve within the torus, right? And that's true for all lines, right? Like I can find these 2 lines that forms the torus. The lines that go in this direction, you go from here, let's say from here. You start here, you go up, you keep going, and then you go to the opposite end of the torus, you jump over here, you go here, you go to the opposite end of the torus, you go here. So that's another one. And then the diagonal over here it's clear. It's another circle because you go like this, go to the opposite end, come back here, and so on. So you realize that every single edge in this graph actually is representing a cycle, which is exactly what I told you, more geometrically here, that I was basically, cutting the torus vertically and horizontally, and each of them are going to be circles, and for each circle, we minimally represent discretely as a triangle and so on, right? Anyway, so
can you try turn it into planar graph, like some planar embedding, so that like there's no intersections going on.
Oh, but you mean more, so doing something specific to this?
Yeah, just try planar embedding.
Yeah.
How does or just planar graph, I guess would work. Does it mean it's not planar, right?
Yeah, I think so. Yeah, it would be very strange if this is a planar graph, right? Because it's a toroidal graph. I mean, clearly, right? It's inscribed on a torus.
I was just searching for minimal triangulations of a torus, so there's some planar graphs. popped up. I don't know.
Interesting. But are they just undirected graphs? Because that's part of the trick.
Yeah, there's like I can put one in chat. I don't know what it makes it.
Yeah, sure. So that one is not a planar graph. That was clear because that it was built as an inscribed graph of a torus.
Maybe that one is like a torus, but at least it's in the paper about it.
Yeah, let me bring it up. That's interesting. Well, that's cool. As I said, I was not claiming it to be the minimal one, but it was certainly one. Yeah, that's the thing is, for our purposes, it is better. So I really needed the one that we can see, because otherwise, I mean, these are fine. In fact, if they can be inscribed on the plane, that's even better, because we can just use a 2D picture. But anyway, for demonstration purposes, having the 3D embedding is also good. Is there a way? I mean, we could just draw this, but did you see a way to get this data?
No, I haven't looked too deep.
Let's see. Triangulation of a Mobius band. Yeah. Yeah, at some point it might be good to. I mean, this is easy to. Oops. I mean, this is easy to just draw, right? I mean, meaning you just put some coordinates and make it something approximate to this, and then just take the graph data of that. In fact, I could try to stress test the hypergraph draw. Just try to draw it like that. How crazy would that be? Let's see. Oops. So, yeah, this is not. I don't have high hopes about this.
We'll just not do it. It's like I'm not even sure if that's the correct. We're interpreting the picture correctly.
Why not? It says minimal triangulation of a torus.
But what does the 2 means? I think it means genus 2. So maybe it's like 2 whole donut.
No, two torus. That's the usual. 2 torus is the torus that we're.
No, in the paper, this 2, I think it says genus 2.
What?
Genus to mean right? Or maybe I don't know.
No.
No,
So
it's T2, it's
T
RP2.
T2 is the torus for sure, 100%. And I mean, and it's kind of obvious from the picture that this is a triangulation of the torus, right? Because it's a plane, two-dimensional, and you have the identified size, and you have only triangles between all the sides, right?
But maybe it's not a graph. It's like, what are the colors? It's like, see that there is a red line. Maybe that's means that you have to identify the top and bottom line together. Like
Oh,
stitch.
that's exactly what you have to do, right? So,
But if you actually want the graph, which is planar, you don't need this. Like
no,
extra.
but the graph. Okay, so
Wait, what's the subscript? X equals T2. T2.
my understanding is that the graphs. Wait. Did this claim that they have did this claim that they have a planar triangulation or just a triangulation?
No, I don't think so.
You don't think it was planar? It was planar, right? Because they said minimum.
Yeah.
I think that's the key.
Anyway, so the idea is that we're looking into triangulated graph. And we have rewriting rules that do homotopy on those.
Yeah, exactly. Yeah. That's the. I'm just curious if. Let's see. So now. Okay, already failed the first edge.
Weird.
Yeah, it's not liking it, not even for one edge. Anyway, so yeah, anyway, so we could take it, but this is okay, this is one triangulation. And so now what we could show, let me go back to could try to show, oops, is whether we actually can get a, so first thing we need is a graph. What is my function? Do I just what? What's going on here? Huh.
Well, edge list returns the actual edges, not thing. You have to map apply list.
Okay. Well, so, and I can actually use the. Okay, so now this is actually a hypergraph in our Padlet. And I'm gonna do. Yeah, that's much better. So let's just try to find some homotopies, right? Like we did before. let's see. So there's a clear cycle. I mean, some of the cycles are odd to sort of identify from the picture, but let's say the cycle, you know, the two triangles that you can see inside the square that are sort of like visually clear, right? You have the 3, 4, 8 and the 2, 6, 7, right? So these right? So let's see what those correspond to. The 1, or is it 2, 6, 7? It's 2, 6, 7, right? It's this triangle. So it's kind of going around the torus, right? And then the 3, 8, 3, 4, 8, it's the other one, right? So the 3, 4, 8 is 3, 3, 4, 8. Right? So it's like that. So it's another circle that goes around. So these are basically two longitudinal cycles of the torus, right? Intuitively. Let's visualize this. So let me define the paths. Yeah, so let's just do.
We just need like a picture of an actual torus and those vertices on the surface of it with the bent edges, right? So we just, the edges, they're actually moving along the surface, like
Okay.
HBT. In this visualization, I think it would be helpful.
Yes, that would be helpful. How do you think it's a quick way to do that?
There's no quick way, but
Okay.
we have to make it later.
Yeah. So let me just say blur path 1. I'm gonna choose blur path. What was it that I said? It said what? 2, 4, 2, 7, 7, 6. Let's go 2, 6. 6, 7, 7, 2. Okay, that's a good sign that we have a cycle. And then similarly, I'm just gonna do the same thing. But instead, I'm gonna do 3, 4, 3, 5, 3, 4, 4, 8. Oops. 8. All right, so let's not go like that. And so path and graph, I'll do in, oh, right there. Messed up the embedding. Interesting. That's my function. Well, I'll just make it again. All right. So hope that's clear. We have our path in our torus. Could also do the 2, but they'll be in a. So let's just, why not show both side by side? That's the same thing. All right. So, okay, clear enough, right? We have the 2, 6, 7 and the 3, 4, 8 paths in our torus. And now what we're gonna do is basically the same as before. We're gonna see if these are homotopy equivalent, right? So the way we do that is basically take the same code here. Just this is kind of a longish thing to look at, but all it's doing is just applying the 3 rules and generating all possible future states. So we're gonna apply it now to simply have to actually what I want. This is what I meant. That's better. Ooh, what is this? Yeah, no, I hyper G. All right. Let's see how long this takes. Shouldn't take too long. So what we're doing right now is generating all the possible homotopy forms of this path over here. So actually, yeah, we're gonna get a lot of states out of this. Let's see. By the way, where at this what was the graph highlight? Is that the
It's highlight graph.
highlight graph? So graph and subgraph, right?
Yeah. You should really use those smart percents that been introduced in the new version.
Okay, well, so how do I do it?
Oh, you type %50. That's the cell that you're referring to.
Oh, and it's gonna keep.
Yeah, and select that graph. Yeah, so that now it knows.
Okay, yes, that's convenient. Yeah. So then what I'm gonna do. Would this work if I just say graph? I specify the thing like what is it? 2.6.
You don't have to specify graphs, just takes edges or vertices. But yeah, you can use graph too.
Oh, I can just specify the edges?
Yeah.
So if I give this a list of edges, that's enough?
Yeah.
All right. 6, 7, 7, 2. But of course, we're still waiting for this, which we know how long it's going to take. Let me abort this for a second. Let me just run it once.
If it takes too much to generate, it would even take longer to render. It's like,
yeah, no, the generate is fine. But I mean, we can see some of the things that happen here. So let me just show this. Oh, what?
Not highlights only the vertices.
So
What if you do
graph?
graph? Maybe. It has to be like a subgraph to highlight edges. Yeah.
What? Why? Why is it highlighting? What? What's up with that? Why is it doing that?
Maybe just supply a list of undirected edges.
List of undirected edges, but that's what I did.
Try subgraph, like subgraph %50, and then list of edges. Maybe it has to be like no, keep the highlighting, keep that as the second argument to the subgraph of %50. Right.
And then like that.
or for subgraph.
Okay. Nice.
Okay, that works. Okay, so yeah, so this is a quick way to visualize it, because obviously in our backlit the embedding is sort of pushing the edges away. It's a good thing because it means that we have clarity when we want clarity, but for this geometric example is a little bit harder to look at. But this here does give you a more or less intuitive thing to understand. So how, for example, can I highlight two with the same, with different colors? That should be easy, right? Like, how do you change the color, you know?
You can, I think you can just wrap it with style, like around
that-
the whole,
Does
around
that
the whole
wrap?
style and color.
Red?
It was already red.
Yeah. Okay. No deal.
Cyan.
And so how do I have to wrap the whole thing with highlight, another one, or can I just list
You
another
can list,
something?
you should put them in the list, I think.
But in a list, you say?
Yeah. Yeah.
Just don't like.
You didn't have to specify styles. It will still choose different styles if you just list different graphs. I think so.
It's the 3, 3, 4, 8. Okay, so well, there you go. That's two cycles in a torus, right? That are visually, I think everyone agrees, clearly deformable into each other, right? Because just push this 4 to the 7 here, you push the 3 to the 6, and you push the 8 to the 2, right? And that makes the two cycles the same.
Yeah, but can that be done by cutting triangular corners off of the path? That's an interesting question. I feel like maybe the rules that you specified have like some implicit fixed point.
Well, but the point is that you see this thing here, you can basically wrap around, and that's like a deformation that just wraps around. So
they're definitely homotopic in the sense of
yeah
on the graph.
This stuff's really just getting interesting. I need to go, but I'll watch the recording from here. Thanks, guys.
All right, thanks.
all right, James, see you later. But yeah, anyway, so with just one application, right, you get things like this, of course, when you compose two paths. But with just one application, we're not going to get to those. But I do imagine, let's see, maybe there's an easier view. I think this view is more explanatory, right? So the idea would be that you eventually get the torus, sorry, this embedding here, right? And this would be very, I imagine, generally quite expensive in a way. So obviously you're generating all these future states without knowing where you're going, right? Like you have all the rewrites and you never know if you're hitting on like the right path. But technically you know that you're gonna, so it's a pretty bad, inefficient algorithm to check for homotopy equivalence. But
Yeah,
the
because it
good thing, I
generates all
guess,
possible like homotopies in this setting. Yeah, it's really
Yeah.
open-ended. And you
and
can,
it's
you
really
can,
unclear. Yeah. From
it computes all this flapping about. It's like as well as the ones that you care about.
yeah. Yeah, well, but and the thing is, some really, like, you get this uncomfortable fact that really trivial cases of homotopy are really difficult to check, right? Because
Well, you could say, all right, you have one path that has all these vertices on it, and you have a target path, let's say, and there's a homotopy if every vertex, but if there was a correspondent, well, I guess if it's a path, then you have like a linear ordering on the vertex sets. In any case, if there's a path from every vertex to a corresponding vertex on the target path, then you could say that there might be homotopic.
well, but that's just checking for connectedness, right?
Mm-hmm.
I mean, sure, like you wouldn't spend time checking for homotopy if the paths belong to separate disconnected components of a graph, right? But
Right.
yeah, but what I'm thinking is that cases where geometrically it's really a trivial case where, I don't know, you have two circles in a plane, right? But they're just far apart. Like they have a lot of edges and vertices in between them, right? To check that these two things are homotopic is super difficult, right? I mean, difficult. It is very expensive with this approach, right? Because you'd have to. I mean, the problem with this approach is it only works when you compute everything, right?
Yeah.
If you just exhaust all the possibilities and you find nothing, then you know they are homotopy equivalent or inequivalent.
Right. So you have basically, the set of all paths, and then this will make connections in that. And then if the set of all paths is homotopically disconnected, then you know that there are discrete units in this like homology group.
Yeah. I guess this is a point about sort of meta mathematics here implicitly, that, which I guess is part of the motivation of infrageometry, is that what mathematically is usually kind of the sort of statement that one seeks, like these two curves are homotopic, and if so, for example, we can build the equivalence class of all homotopic curves and things like that. Like mathematics just has this way of condensing and crystallizing that kind of information. In this context, you would need like this unreasonable amount of computing power to actually process it, right? So then the question is, could you ever find a way to identify patterns that are going to be mathematically relevant before needing to exhaust all the rewrite system? Because
I mean, one thing that could be more efficient is sort of especially if you have a fixed point, you can commute like homotopy groups.
Yeah.
If you had a fixed point, you say like, well, here's a curve, and you wanted to shrink it down to the most like geodesic, the shortest path that connects these two endpoints or the same endpoint or whatever. And so you only apply rules that reduce the length of the curve and see what if there's any confluence there. You say, okay, this is the canonical path after I've cinched up like my rope or whatever. And then you could, it's basically picking out coset representative in the homology group.
Yeah.
By having like geodesic finding rules that morph these paths.
But you would say something like pick a base point or any two fixed points, and then essentially trace a random fixed length path between those, and then apply rewrites to see if you can apply rewrites that only shrink or the form, right? Because that's an interesting thing actually. That the fact that from the point of view of the rewriting, you have like it's basically like the whole picture, right? Like you have the conservative rule, the generative rule, and the reductive rule. So it's easy by hand to just say we're going to deform our path in a way that preserves its length, reduces its length, or increases its length strictly, right? And you can be, preserve or reduce or preserve or increase or only increase or so. So I guess if you begin with a random choice, it could be like this idea of like as you said, right? Basically you throw a rope. I mean, if it's just a fixed point, you just like find any loop around your path, which is relatively easy to do, and then you just tighten it, right? Which is the very intuitive process of like kind of cinching a rope and see if you eventually only get the rope or you actually get something stuck in the way, right? So you have like a handle in your space. You have some non-trivial homotopy generator.
Yeah.
Right. Yeah, that's intuitively interesting. Just wonder if that makes sense, like in practice. What does it mean to generate a random?
Also, are these rules sensitive to directed versus undirected?
No. So right now these rules. Okay, so these rules are a little bit hacky in the sense that to use our Padlet to do the rewriting, we assume that undirected edges are sort of space stuff, and directed edges are path stuff, right? So yeah, it's yeah, not clear.
Yeah, it's like it occurs to me that you don't want to compute homotopies for edges that are just spatial. Like you want to make distinctions. You want to have this like static graph or hypergraph with spatial edges, and then you have this path which can mutate according to rules based on the underlying topology. You don't want to go into the space of using the rules to morph the space itself. When computing
the rules. I mean, the rules are clearly conservative with the space itself, right? Like the undirected, if you strip out the directed edges of these rules, you just get identity rules, right? Where input and output are the same thing. It's the identity rule. You see what I mean?
Well, I mean, okay, so like if you applied this rule,
if I remove
the other rule, I guess. Okay, you have like this one edge, and then you can, instead of doing this, you can go around the corner and make it longer, right? But if you are uncareful, then like maybe like the second time, Like you wouldn't want to move the edge on that left figure 1, 3 to 1, 2, and 2, 3. Although technically, if the other rule, the path bulge, like you wouldn't want to path bulge that spatial path.
Yeah, well, I mean, that's what I'm saying, that these rules, you're right, you wouldn't, but these rules are okay for that because they don't see, like, they don't see the space, because everything undirected is just the identity rule. Like it has no effect on undirected edges, right? Which you can see explicitly by if you remove, like you can just inspect it, right? You can remove the directed edges from these rules, and what remains is the identity rule, the do nothing rule. It's just 1 to 3 edges, 1 to 3 edges, nothing's changed. So it is technically a rule in some sense. It's a rule, right? Like, but its application is always going to give to the same state, right? So for all intents and purposes, you don't have a rule when you have that rule, because if you want to consider those as rules, you have as many rules as there are hypergraphs in the universe, so to speak, and you have as many rule applications as there are sub-hypergraphs of any hypergraph in a larger hypergraph, right? So it's...
Well, okay, question. Like, what would happen if you looked at the effect of applying path bulge rule to a undirected triangular graph?
It will find no matches. It will just find no matches because this is asking for at least an undirected edge and a directed edge together, right? So if your state,
so the rule is sensitive to whether or not a path is directed or undirected.
Oh yeah, absolutely. Maybe, oh yeah, sorry. Maybe my screen's, yeah, because the arrows are very small.
No, I see the direct. Thank you.
Yeah. So the rules are absolutely sensitive to that. Like that's crucial. That's why it works. That's why you can claim that you're doing something like homotopy, because I mean, you could always label.
Okay. You're looking for specifically ordered, unordered, or whatever.
Yeah.
In the
So you could always, by the way, you could always do this undirectedly. You could just do undirected path homotopy simply by using labels. You just have an unlabeled edges, and then you just label your paths, like color them somehow, right? You just say this label, path 1, name whatever, path 1. This is path 2, name path 2, and these are the labels. And so your pattern matching cares that you only rewrite the things with the same label, right? And in fact, one can remember that I had in the previous section this function here, kind of like an almost anecdotally to do compose, like this compose paths function. Actually, you can instead of using this as a function, you can do it as rewriting, because you can imply a rule that demands that you have a path of length 2 where the first edge is labeled something and the second edge is labeled something else, right? And if you demand this, you would end up composing paths together, right? So anyway, that's just as a side comment. But I think this is good. As I said, I just wanted to run with you the idea that we want to look at these things in a bit more detail, and mostly brainstorm around this idea of this is ridiculously inefficient for it to actually work as a means of computing homotopy, but at the same time it somehow feels right, because your rules really encapsulate what you think homotopy is conceptually, and mathematics is so it kind of illustrates how mathematics is a game of reducing complexity dramatically, right? Like all the large swath of computations you have to do to check that two curves are homotopic. If you have the right setup of definitions, you could just mathematically argue and arrive at the same conclusion without going through all the actual deformations, right? Which I think in a way is analogous to what Stephen has mentioned at times about physics and what physical law is and so on, right? Where you have the actual evolution of the universe. If you imagine, this is a typical statement of, imagine the Earth moving around the sun. The Earth is this extremely complex thing with billions and billions and billions and billions of atoms and complicated things on top of it and so on. But if you look from far away enough, the center of mass position of the Earth follows this extremely simple equation of motion, right? And so similarly here, maybe you could say, yeah, the phenomenon of homotopy is this very nitty-gritty thing where you have all the detail of how things move atomically, like between edges and being rewritten and shrinking and bulging in like all possible ways. But if you look from far away enough, quote unquote, which in this context would mean something like, if you have the right mathematical axiomatics and the right mathematical distillation of the phenomenon, you might be able to just shortcut and say, I don't have to go through all the details of the evolution of the rewriting. I just know that if this is the case, say, I know that there are no holes in this space. I have this information that gives me kind of a law that in this space, all your curves are going to be homotopy equivalent, right? And so you collapse all that complex evolution to get to the same predictive in the state without having to run it fully, right? Like, obviously, all this idea of like computational reducibility in this case and so on, right? So anyway, it's just another instance of this kind of concept, I think, with this very special example of homotopy as a model for things that can run in the current hypergraph backlit and in what would be the infrageometry thing. So, yeah. Any other suggestions or ideas?
How did you get that graph, by the way? You
Which one?
discretization, right? Discretize the torus itself, the graphics.
Yes. Yeah, I should have kept maybe my working code here, which I think I just used discretized surface. That?
Discretized graphics or region.
Yeah. Yeah, this was the whole thing that I was asking you about, because I couldn't get the resolution very low. They would go to some minimum resolution and it would start to do weird things. Like the actual vertex count was always high.
Yeah, it's like smooths out the edges, tries to too many triangles. Exactly.
Yeah, it just always tries to, it never goes like low poly, it never goes like PlayStation 1 era low poly graphics.
Yeah. I still don't know how to do it. Maybe there's a way.
Yeah. But it was fun. I mean, to be honest, in retrospect, I'm glad that it didn't work, because I don't know why I enjoyed it so much, but I really enjoyed computing like these triangles.
Yeah, it's very zen.
Yeah. It was like, I just want the equilateral triangle that has an equilateral triangle inside that is exactly 1/3 of the length in the side, right? And only that information is enough to specify everything else, because there's no degrees of freedom. So that from the get-go that you're going to get all the coordinates of your points if you want to. It's just a matter of like crunching through the equations. So, I mean, and here crunching through the equations really just means like square rooting like a fraction or something like that. It's like super kind of secondary school homework kind of thing. But yeah, it's very zen to like, oh no, I picked up a square root of 2. Okay, so now he's part of the family. Oh, I picked up a square root of 3, so now he's part of the family. Like you're always doing all these exact computations and trying to simplify as much as possible. And in the end, you get like this, like 3 times square root of 5 minus 9 times square root of 3. It's like super super satisfying stuff, right?
We need some stereometry tools in the language, because we have the 2D geometry. You could have like solved this by specifying triangles in 2D, but I think there is no 3D version that does this automatically.
Right.
You can construct like geometric scenes and ask questions like what is the angle, and
Right.
prove theorems about them, but it doesn't work.
Yeah, that's right. So yeah, anyway, that was it. As I said, I didn't have much time to progress on this. I was busy with all other kinds of stuff. Just to mention, for our viewers, it's not directly related to infrageometry, but it is related to geometry. We had a conversation with Garrett Lisi about the possible connection. I just want to mention it here because I find it scientifically stimulating, and it's a bit of research that anyone listening can be compelled to do on their own, because it's really easy exercise. And I haven't done it myself, because when I have easy exercises, I usually just keep them for when I'm feeling down or something, I just do them. And it's like, because to bring myself up. So the question is as follows. It's about ternary algebras. It's about 3D algebras. So you know how in 3D geometry you have your cross product as your as the infinitesimal representation of rotations. What that means is that you can imagine having any object in 3D and slightly moving it in all possible independent ways. And so what you find is that all the possible ways in which you can move things infinitesimally, rotate things infinitesimally, behave like an algebra of 3 dimensions. And the 3 dimensions are not the 3 dimensions of space. These are related that it's in 3 dimensions of space, but the 3 dimensions are the 3 possible ways in which you can rotate something, right? So you can think of the 3 infinitesimal rotations about each axis. So there's the 3, right? But anyway, so the point is, what you get algebraically out of this is the so-called SO3 Lie algebra, right? Is the cross product Lie algebra that everyone learns about in high school. When you go in high school, when you learn about it, many times you learn this determinant formula, right? Where you put your basis vectors I, J, K on the top row, and then you do sort of A1, A2, A3, and then B2, B1, B2, B3, and the others. And then when you learn the determinant formula, you know how to compute that. And it turns out that the components that you get out of that are the components of the cross product, right? So, okay. So the idea is, okay, what does the cross product actually compute? So we know that the norm of the cross product is related to the surface area of the parallelogram. Forget about it. I don't care about the norm. I just care about the direction, right? So the direction of the cross product is, well, right-hand rule, right? Like that's how you get it. So what is it? It is, you take 2 vectors that represent 2 directions in an order sense. You check if they are linearly independent. If they are linearly dependent, you get 0. Okay, fine. If they are linearly independent, then they span a plane. So a plane is a codimension 1 subspace of 3 dimensions. Therefore, we know that there is a unique 1-dimensional orthogonal subspace to that. So we know that there's 2 directions that can orthogonally complement those 2 vectors that we introduced. So because you are in an oriented space, because you've chosen some orientation, you know that there's a unique positively oriented vector. So you take those 2 vectors in the order given, and you pick a 3rd vector that is in the direction of this unique orthogonal direction and in the unique side that makes the whole 3 vectors positively oriented, right? So that is the prescription of how you compute a cross product without doing any algebra, right? That's just the geometry meaning. So if you realize, and then there's this almost this urban legend of the math undergrad students and physics students that their teachers tell them, you can only define the cross product in 3 dimensions. And the advanced students know that actually in also 7 dimensions you can do it. And then the really advanced students know that this is directly related to the Cayley algebras, to the division algebras of like the real complex numbers, quaternions, and octonions. And it's like they're getting super in the cabal of numerology of what this means. And then someone comes along and says, wait, you can actually be much simpler than that, and you can do a cross product in any dimension. And it's like, okay, what is the story here? Well, if you walk through the steps that I just described earlier, at one point did I use that there were 3 dimensions? So no, you did use it at one point, which was the moment that I said that I input 2 vectors so that there is a unique, or so if they are linearly independent, they span a codimension 1 space. And you say, okay, so what if we are in a different dimension? Then all you have to do is specify as many vectors as you need to span a codimension 1 subspace in that space. Okay, so let's run the experiment in dimension 2. So what happens in dimension 2? Dimension 2, you need only 1 vector, non-zero in this case, to specify a direction that has a subspace that has codimension 1, because that's just dimension 1. 2 minus 1 is 1. Okay, good. So what is the unique orthogonal positively oriented direction of a vector in the plane? Well, there's just rotation by 90 degrees, right? It's the counterclockwise rotation of 90 degrees of a vector. So for those of you who studied mathematics before, that is what's called the complex structure of the plane, right? That's essentially multiplication by I with the complex numbers, right? So it turns out that the cross product in 2D is the imaginary number, right? Like it's multiplication by the imaginary number. So interesting. What happens if we go to 3 dimensions? Well, to 4 dimensions. So we went 1 dimension lower. The cross product made sense there, and it was not only made sense, but it was the all-important complex numbers is what you got from that. So you go to 4 dimensions now. The only thing that changes is that you need 3 vectors to specify your codimension 1 subspace. And so you do that, you realize that you need to put 3 vectors in your product, and then you end up with a ternary bracket of vectors. And I say bracket because it's fully antisymmetric, because every time you swap the positions of any 2, the orientation globally changes to a minus sign. So the thing is, that is what it's called a ternary Lie algebra. And the ternary product satisfies the Jacobi identity as you expect, but instead of having, the typical x, y, z, and then x on y and z, and then y, and then x and z, which is a typical Jacobi identity, because now you have 3 arguments in each, you have sort of 3 terms and things associated in the right way. So it's an analogous thing. And you can just check by hand if you wanted. In Mathematica, you just do it very easily, just check that holds. So here's the question. So these are all background. And now, what's interesting about this is our space-time. So this construction, of course, works in any inner product space. So if your space has an inner product of any kind, doesn't have to be positive definite, could be Lorentzian signature, could be any signature, right? You can do this construction because all you require is a sense of orthogonality, right? And so if your space has a sense of orthogonality, you can make these constructions happen. So space-time turns out to be one of such cases, right? So we were in conversation about this, just brainstorming a bit, and then Garrett just said, well, we in Riemannian geometry or pseudo-Riemannian geometry, we already have a tensor that looks like the ternary Lie bracket. Because this ternary Lie bracket, this cross product in 4 dimensions, is exactly something that takes 3 vectors and gives you a vector. So as a tensor, it has 1-3 rank, right? It puts out a vector and eats 3 vectors. So Garrett just pointed out, yeah, that we have a tensor, a very famous tensor that already does that in Riemannian geometry, which is the Riemann tensor, right? Just the Riemann tensor has exactly that behavior. And so the question, and this is the homework for anyone who wants to try, the question is the Riemann tensor in 4 dimensions, when antisymmetrized, because the three arguments of the Riemann tensor are not fully antisymmetric. They're antisymmetric in blocks, but not fully on the 3.
So it's a rank 3 tensor?
It's a rank 1-3 tensor.
So it spits out a vector given 3 vectors as input.
Exactly.
Okay.
Yeah. So yeah. I mean, technically, conceptually, the Riemann tensor is a endomorphism valued rank 2 tensor, right? So it's 2 vectors and it spits out an endomorphism, which is a thing that eats a vector and spits out a vector, right? So the thing is,
okay.
Yeah. So the thing is, so that's why you have to anti-symmetrize, possibly. So you bring all the three arguments to the same level. So you anti-symmetrize them. So the question is,
Wait.
Is-
You put in two vectors and then you get a rank 1-1 out.
yeah, that's right.
Okay.
That's right. And then, so that's why it's the same thing as rank 1-3 tensor, right? So it is antisymmetric in those two arguments, right? In the two arguments that you put in to get a 1-1 tensor, it is antisymmetric. The curvature is defined, Riemann-Tensor is the curvature tensor, and is defined as the deviation between the Lie bracket of covariant derivatives and the commutator of the covariant derivatives, right? As operators. So that's, it measures that, and it is surprising that it's a tensor. So it's non-trivial that it's a tensor because it's made of non-tensor things. Like the covariant derivatives are not tensors, right? They're not C-infinity linear. Anyway, that's beyond the point. The point is the Riemann tensor with the three indices, the three bottom indices, antisymmetrized, so that you just see a rank 1-3 antisymmetric tensor? Is it a Lie algebra in this sense, right? Does it satisfy the Jacobi identity? It's a trivial question. You just do it, like put it in, antisymmetrize it, and ask, does this satisfy the Jacobi identity? So, but the fun exercise is to actually try to do by hand, because if you want to prove it in general, you would have to just use the formulas. You won't be able to like compute some Riemann tensor of some metric and then see if it works, because if it works, it might just be coincidence that it works for that metric, right? So anyway, we got quite I don't know, wide-eyed with this question, because it was suddenly, wait a minute, this thing that and it was very surprising to me, because I've known the Riemann tensor since I was, I don't know, like 18 or something, or 19, and just having spent so many years thinking about ternary algebras, and then realizing, wait a minute, the most famous tensor in Riemannian geometry has the rank of the four-dimensional Lie algebra, the four-dimensional cross-product Lie algebra, which happens to be ternary, which is exactly right for what you want. And then we started discussing possible connections to the 1+3 decomposition of space-time, because there might be something juicy going on here, because it only works if it works, or if it has something interesting to tell us. Maybe it doesn't work in general, but if it has something interesting to tell us, it's only going to work in 4 dimensions. So in 4 space-time dimensions, in 4 full manifold dimensions. So and the construction basically sort of telegraphs the 1+3 decomposition, because it has to be, you can only really construct the product in the directions that are space-like to get a time-like thing, right? So this Lie product, in a sense, is a very familiar construction to a lot of people, because it's basically the idea that if you specify fully your rulers in your physical experiment, that means that your time clock is also fully specified, right? So that's the enticing premise here is that physical phrase I just said, which it only involves rulers and clocks and whatnot, that has a Lie algebra structure. We know that. That's a fact. So in the history of physics, it's been a big industry to exploit when there were Lie algebra structures somewhere. They were always binary, and that was always the point. This one happens to be ternary, and we don't know much about these ternary Lie algebras, but it's there. It's actually there. It's sitting, maybe waiting to be exploited, as we exploited the binary ones. So anyway, I thought it was a fun thing, and it has a piece of homework attached in case anyone wants to get their hands dirty with the covariant derivatives and all kind of computation, which are fun. These things, if you've learned the tensor calculus of relativity, these things are fun. Like, it's very satisfying, like simplifying. So, but yeah. Anyway, I just wanted to.
If you want nowadays, you could just like there's array symbols that are symbolic things that you can actually now differentiate in the language. We can try it out. So we don't have. Yeah, so we don't have to use some external package to do symbolic generativity stuff in the tensors. You can maybe do it like in built-in stuff.
That's right. I was actually thinking about that when I mentioned it to Garrett. but that's the symbolic array stuff right now does derivatives, right?
Yeah, well, yeah.
But does it do covariant derivatives? Like,
Well, you can define it, I guess.
I
Right?
guess you can, but it would, but it would be very, very cumbersome to define, right? Because you would, if you want to define it with arrays, you would have to define the Christopher symbols, right?
Yeah.
And the
Yeah, the only problem with those symbolic arrays that I raised a bunch of times that they still doesn't have different. They don't differentiate between covariant and contravariant indices, which is very annoying.
that okay, yeah, but I wouldn't worry too much about that. I'm more worried about the how you implement a covariant derivative, because the way you do it, like by hand, right? If you want to do it with arrays, like with matrix expressions, you define a covariant derivative as the derivative plus the contraction with the Christoffel symbol, right? But the Christoffel symbol has a very special behavior under derivatives, right? So you have to impose
some ways you can specify also the symmetries of your tensors. I think I don't. Yeah, so you can say that this is like this tensor is antisymmetric in this, and this is symmetric in this, and this is, and maybe this is taken into account when you take derivatives and stuff.
Yeah, but I mean, symmetry is a whole different thing than the fact that Christoffel symbols differentiate in they satisfy differential equations that are very specific, right? Like, I don't think
this is like a condition, I guess. It's an assumption in the language. You specify the equation that has to be specified, then you simplify whatever you want to simplify using this assumption.
maybe,
and ideally it could work. I don't know.
Maybe. Yeah, maybe it could work, but yeah. But I think it would be easier. Well, I don't know. Maybe it could work actually. But I think it would be easier to just symbolically implement tensor calculus. Just period. Just tensor calculus proper. Like intrinsic tensor calculus, just with the covariant derivative, lead derivative, contractions, and so on. And then just operate with it and see if you find, like, simplify with it. But anyway, but it would definitely be a very good stress test, right? If you can actually compute, I mean, not even that, because you don't know if this is going to work out, but like the Bianchi identity or something. If you could check the Bianchi identity of the, not even that, let's say just the Lie bracket property of the covariant derivative. Wait, yes. If you can check the Lie bracket property of the covariant derivative, which means that the Lie bracket of the commutator of two covariant derivatives is another covariant derivative, right? If you can check that with the symbolic array, I would say then it's good to go. Like it can do things, but yeah, I don't know how useful it is when you have to tell it super explicitly that this is what the Christoffel symbols should do in all the glory of all the indices. I don't know.
Yeah.
But anyway, fun stuff. Anyone in the community wants to get busy, and definitely you can add me in the Discord server. As I always say in these live streams, if you are not on our Discord server and you'd like to join kind of the scientific effort more or less directly, you can always come to our, so let me just post the link to the community here. So yeah, it's yeah, if you want to get busy with that piece of homework, just add me, and I can give you a precise statement of it. I think I'm saving it for sometime next week when I'm feeling down. It's like, okay, sit down, put the timer. 20 minutes should be enough to complete the computation, and then just see if. But yeah, anyway, guys, thanks a lot for this. So I said there's a link in the chat. I guess we see you next week.
Mm-hmm. Thank you, Carlos. Thanks for tuning in. See you next
Yeah,
time.
thank you, everyone.